Hello! This video will give you a first basic introduction to Interface Equilibrator, showing you how easy it can be to use it. For example, you can calculate the shape of a droplet wetting a certain solid substrate, or the shape of a meniscus between two fluids inside a certain container. Let's start by launching Interface Equilibrator. I assume that you have already downloaded and installed Interface Equilibrator on your computer, and that you have activated a license to use it. If you don't know how, I will show you how to do that in another video. Once we launched Interface Equilibrator, we can click this button to create a new configuration. This opens a new form, which provides the environment where you can set up and execute a new simulation. Let's start with a simple example. We want to calculate the shape of a droplet wetting a flat, solid substrate. The first step is loading the triangular mesh that will represent the shape of our droplet. We click this button to add a new fluid-fluid interface mesh in our configuration. There are several options you can use to load a new triangular mesh. In this case, we select Built-in Meshes and then click Next. We need to choose a triangular mesh with the same topology of the fluid-fluid interface that we want to simulate. To simulate a droplet wetting a substrate, we select the topology of a sessile droplet. This control sets the initial volume of the droplet. The default length unit is micron. Later, I will show you how you can change it. We leave 1 as volume of the droplet, and then click Load. This is the triangular mesh you just loaded. It has the shape of a cube, but without the bottom face, which is a correct topology for the fluid-fluid interface we want to simulate. To define the solid substrate that is wet by the droplet, we'll load another triangular mesh to represent such a solid surface. By clicking this button. In this first basic example, we want to consider a flat substrate. So, we select again Built-in Meshes. And then we select the flat plane mesh. These controls allow you to tune the size and number of vertexes of this mesh. We leave 2 vertexes per side, and we choose a size large enough to contain our droplet. We now loaded this new gray mesh, which we will set as the solid substrate of our droplet. Coincidentally, its initial position is already where we wanted it to be. That is, at the droplet's base. Otherwise, we would have needed to translate this new mesh to the desired position. We have loaded all the meshes that were needed to define our system. The last step to do is selecting the constraints for the fluid-fluid interface mesh boundaries. In this example, our droplet has only one boundary, that is this line here. The boundaries of the fluid-fluid interface meshes are the 3-phase contact lines of our system. In this panel on the left, you can find a tree diagram showing the meshes loaded in the configuration. And you can also see the boundaries of each fluid-fluid interface, only one in this case. Assigning a constraint to a boundary means specifying the solid surface on which that boundary is allowed to stay. In this example, the constraint we want to assign to the boundary is the flat plane mesh. For selecting the boundaries constraints, we click this button here. In the form that is opened, we can find a list of all the boundaries currently in the configuration. In this case, only one boundary. We select it. This shows us its available constraints. We select the desired constraint for this boundary, that is the solid surface mesh. Then, to confirm the selected constraint, we click this button. We can now close this form. Once a valid constraint is assigned to each boundary, it is possible to launch the equilibration. That is, the simulation to calculate the equilibrium shape of the fluid-fluid interface. As a matter of fact, the Start Equilibration button is now enabled. You can also see that the boundary node in the tree diagram is no longer in bold font, to indicate that a valid constraint is selected for it. Before clicking the Start Equilibration button, let's save the current configuration. For later convenience, If I now exit from the current configuration, by clicking this button, I can reload a configuration that I previously saved. Let's now click Start Equilibration. Interface Equilibrator has calculated the droplet's equilibrium shape. And, in this process, the fluid interface mesh was automatically refined. The obtained equilibrium shape is a spherical cap, as expected. The volume of this spherical cap is equal to the volume of the shape that the fluid interface mesh had when we started the equilibration, which is, in our case, 1 cubic micron. The geometric contact angle of this spherical cap with the solid surface is 90 degrees. This is, indeed, the value that is assigned by default to the Young's contact angle when we constrain a boundary on a solid surface. I will now show you how to edit this value. Let's first reload the initial configuration that we saved before. Then, in the tree diagram, we right-click the Solid Surfaces node, and then we click the Edit Theta link. Theta is the symbol for Young's contact angle. In this form that was opened, we can edit the value of the Young's contact angle of the solid surface mesh. For example, we set 150 degree. The value of Young's contact angle is always measured in the fluid below the fluid interface, as illustrated by the sketch in this form. To discern which is the fluid below a fluid interface mesh, you can show the normal vectors to the fluid-fluid interface meshes by clicking this button. These purple arrows are the normal vectors. Their orientation is always towards the fluid above the interface. So, the fluid below is the fluid inside the droplet. Therefore, since we selected 150 degrees as Young's contact angle, this droplet likes to wet the substrate less than the fluid outside. As a matter of fact, by launching the equilibration, we see that the droplet's equilibrium shape is a spherical cap with a larger contact angle than before. Precisely 150 degrees. If you want, you can also assign a different Young's contact angle value to different facets of a solid surface mesh. To show you how, let's reload the initial configuration that we saved before. Then, we add a patch to the solid surface by right-clicking the solid surface node in the tree diagram, and then by clicking the Add Patch link. A new node was added in the tree diagram to indicate that the solid surface now owns one patch. To select which facets of the solid surface mesh will belong to this patch, we need to right-click the patch node and then the Edit link. This launches the tools that we can use to assign the facets of a mesh to one of its patches. By clicking this button, we activate the tool to use the mouse cursor to select individual facets. By clicking on a facet, I select it. And by re-clicking on a selected facet, I deselect it. I can also drag the mouse cursor to select multiple facets. To drag the 3D view around with the mouse, I need to deactivate the Select by Mouse functionality. Let's assign one facet to the patch. So, we leave one facet selected and then we click the Confirm button. As indicated by the different color, this facet is now assigned to the patch of the solid surface mesh. To edit Young's contact angle on the solid surface mesh and on its patch, we open the same form we used before. We set Young's contact angle outside the patch to be 60 degrees. For the patch, instead, we leave 90 degrees. So, the droplet prefers to wet the facet not assigned to the patch. Let's confirm these values and then start the equilibration. The droplet is unstable in between the two facets and moves to the facet with the most favorable wettability. However, the droplet has not enough space to form a spherical cap. So, the droplet shape deviates from a spherical cap and part of the droplet spills over the patch. The contact angle is 90 degrees inside the patch, and, instead, 60 degrees inside the other facet. If you click this button, you move to the top view. And if you click this button, you can see the height profile of the droplet in contour plot mode. So far, we calculated the droplet's equilibrium shape only on flat substrates. To consider curved substrates, we simply need to load a mesh with the substrate shape. Let's see an example. First, we reload the previous configuration. Then we remove the flat solid surface mesh by right-clicking on its node and then remove. We now want to load a curved solid surface mesh. You have various options to load a new mesh, like an external mesh saved in the STL format. In this example, we will load one of the built-in meshes of Interface Equilibrator. There are several built-in shapes available, and each has tunable parameters. We select the cylinder, and then we regulate its aspect ratio and size. And then we click Load. The cylinder was loaded. Now, we need to move it in the desired position. Let's say we want to calculate the droplet's equilibrium shape when it is wetting the side of the cylinder. Then, we need to rotate the cylinder and place it below the droplet. To rotate a mesh, you need to right-click on the mesh's node in the tree diagram and then click Rotate. From this form, we can select the desired rotation, possibly combining rotations around multiple axes. To place the cylinder horizontally, we rotate it by 90 degrees around the x-axis. We now need to translate the cylinder in the z direction so that the droplet is located at the cylinder's side. So, we click on Translate. Then, in the form that was opened, we select by how much we want to translate the mesh in z, and we click Confirm. We now need to set the cylinder as the constraint of the droplet's boundary. The form for doing this can also be opened by right-clicking the Boundaries node and then Set Constraint. We select the cylinder as constraint of the boundary and then click Set Constraint. And by this button, we can launch the form to edit the value of the cylinder's Young's contact angle. Let's set, for example, 60 degrees. Notice that when the droplet's boundary was constrained on the cylinder, the boundary's vertexes were moved on the cylinder's surface. Indeed, when you select a solid surface mesh as the constraint of a boundary, the vertexes of that boundary are automatically moved on that solid surface. In the previous example with the droplet on the flat plane, we did not notice this because the vertexes of the boundary were already in the flat plane. We now click Start Equilibration, and the droplet's equilibrium shape is calculated, this time on a cylindrical substrate. As expected, the droplet's equilibrium shape has a geometric contact angle of 60 degrees along the whole three-phase contact line, which is now embedded in a curved substrate. To simulate a fluid interface with a different topology, the procedure is very similar. As example for this tutorial, I will consider a capillary bridge between two solid spheres. Let's start a new configuration from scratch. Let's add a new mesh as initial fluid interface mesh. This time, we want to start by selecting the closed cube as the mesh initial shape. Then, we will edit this mesh to create the desired topology. The loaded mesh is a closed cube, so it has no boundaries. As indicated also in the tree diagram, where no boundary node appears under the node of this fluid interface mesh. We now edit this mesh, such that its topology becomes that of a capillary bridge. For this, we right-click the mesh node and then remove facets. These tools are very similar to those we used before to edit the patch of a solid surface mesh. This button allows us to select individual facets of the mesh. Then, once we click Confirm, those facets will be removed. Let's select these two facets. And these two facets. And then we click Confirm. By removing these facets, we created two holes in the mesh. Now, the mesh has two boundaries. Some of the facets of the mesh were split. This was an automatic edit to ensure that single facets do not connect two separate boundaries. In the tree diagram, two boundary nodes have appeared under the node of this mesh. To avoid confusion, we will now highlight these two boundaries using different colors. For doing so, we right-click on the Boundaries node, and then we click Graphics Settings. For this boundary, we select Use Settings below, and then we select a different color, red. We also change the name of the boundary to remember that this is the red boundary. Let's now do the same for the other boundary, except that we use the green color for it. The two boundaries are now highlighted with the color that we selected, and their names have been updated in the tree diagram. We will now load the two solid surface meshes on which we will constrain these two boundaries. So, let's click Add Solid Surface to load the first one. Then, we select Built-in Meshes, and we select the spherical mesh. As sphere radius, we set 0.5. And then we click Load. The spherical mesh was loaded in our configuration. We now want to position it opportunely. Let's say we want to constrain the green boundary on this solid surface. So let's launch the tool to translate the spherical mesh. We want to translate the spherical mesh in the Y direction and in the Z direction. We select an opportune displacement length in both these directions. And by clicking Confirm, the sphere is moved where we want it. We now repeat the same procedure to add the second sphere, on which we will constrain the red boundary. This time we select a radius of 0.8. So, this sphere is larger than the other. Let's then translate to the desired position also this sphere. And we edit the names of the two spheres to remember which boundary is to be constrained on which sphere. Now, we need to select these spheres as the constraints for the two boundaries. So, let's click the button to open the form for doing this. This time, two boundaries are in the list. We select first the red boundary, and we constrain it on the sphere we marked as red. When we set the constraint, the boundary's vertexes are automatically moved on the sphere's surface. We constrain the green boundary on the other spherical mesh. Let's edit the value of the Young's contact angle on the two solid spheres. By clicking this button, we open the form to edit the contact angle of the solid surface mesh that is currently selected in the available constraints. Let's set the contact angle of the sphere with the green boundary to 70 degrees. Then, we select the sphere with a red boundary, and we set also its contact angle to 70 degrees. The newly set values for the Young's contact angles are also indicated in the tree diagram. The fluid below the interface is the fluid inside the capillary bridge, as indicated by the normal vectors. So the contact angle of 70 degrees is expected inside the capillary bridge. Let's then start the equilibration. We have now computed the equilibrium shape of the capillary bridge between the two spheres, with a contact angle of 70 degrees. By following an analogous procedure, we can easily simulate the equilibrium shape of droplets and capillary bridges with any topology, and wetting solid surfaces with any geometry. In the examples considered so far, the effect of gravity on the shape of the fluid-fluid interface was not included. If you are simulating a system with a sub-millimeter scale, This is usually a good approximation. However, for larger systems, gravity might become important. I will now show you how you can easily include gravity in the calculations. If you click this button here, you can find the settings used for the equilibration. The first tab of this form shows the experimental parameters used in the equilibration. These parameters regulate the physical and chemical forces involved in the simulation. The gravity checkbox is now unchecked, meaning that the gravitational force is not active. To include gravity, we check it. Now that gravity is activated, you can edit the parameters that regulate gravity, that is, the mass density difference between the two fluids, the gravitational acceleration modulus, and the interfacial tension between the two fluids. The combination of these three values determines the value of the capillary length, which is the parameter shown here. By editing these parameters, we change the capillary length's value, which determines how gravity affects the shape of the fluid interface. If the capillary length is much larger than the scale of your system, then gravity is negligible. Instead, if the capillary length is comparable to the scale of your system, then gravity does affect the equilibrium shape of the fluid interface. With this control, we can change the default length unit in the configuration. Since we want to consider an example where gravity affects the fluid interface shape, we shift to millimeters. Now the default length unit is millimeter. We confirm these values, which are realistic values for an average liquid air system. Let's consider again a Sessile droplet on a flat plane. As volume for the droplet, let's use, for example, 100 cubic millimeters. Since the capillary length of our system is roughly 2 millimeters, this droplet should be large enough to feel the gravitational force field. Since we want to use a simple flat substrate for the droplet, as an alternative to loading the flat solid surface mesh, we can select the Displace Only X and Y analytic constraint. When this constraint is selected for a boundary, the boundary's vertexes can move only in the X and Y plane where they currently are. So, effectively, we are constraining the boundary on a flat plane. We click the Set Contact Angle button to edit the value of the Young's contact angle on this analytic constraint, like we do for solid surface meshes. Let's set it to 60, so the droplet likes to wet the flat plane more than the fluid outside. Let's then launch the equilibration. The droplet's equilibrium shape appears to be still close to that of a spherical cap, possibly slightly flatter. This means that gravity is having a small effect on this droplet shape. Let's then try to calculate the equilibrium shape of a larger droplet. For example, with a volume of 1,000 cubic millimeters, that is 10 times larger than the previous droplet. We constrain the boundary of this droplet on a flat plane with a Young's contact angle of 60 degrees. So, this system is identical to the previous one, except for the droplet's volume being 10 times larger. After launching the equilibration, we see that the droplet's equilibrium shape is now much flatter than before, strongly deviating from that of a spherical cap. That's because the droplet is now much larger than before. The direction of the gravitational force field is opposite to that of the z-versor. Therefore, if we turn the sessile droplet upside down, we should obtain a pendant droplet. So let's try this. We consider again a droplet wetting a flat plane, but this time we will place it upside down. As volume for the droplet, let's set 80 cubic millimeters. To flip this droplet upside down, we open the form to rotate the mesh. and then we rotate the mesh by 180 degrees around the x-axis. As a result, the mesh has been flipped with its boundary towards up. Let's use again a flat plane with a Young's contact angle of 60 degrees as constraint for the droplet's boundary. We can now start the equilibration. The equilibrium shape of the droplet is now that of a pendant droplet. For this droplet volume, the droplets appears stably attached at the flat plane. That is, gravity is not strong enough to pull down the droplet from the solid surface. However, for a slightly larger droplet volume, the pendant droplet might no longer be stable. Let's try it. So, this time, let's set 90 cubic millimeters as volume. Then, again, we rotate the droplet so that its boundary is towards up. And we constrain the boundary on a flat plane, setting a Young's contact angle of 60 degrees. So, the system is the same as before, except for the slightly larger droplet volume. Let's see what happens after launching the equilibration. Eventually, it does seem that gravity manages to pull down the droplet. So, I did pause the equilibration, since at this point it is clear that the pendant droplet is not stable. If I let the equilibration resume, gravity will simply keep pulling down the droplet. In other words, no equilibrium shape exists for this configuration. Thank you for having followed this video. For more information and for other tutorial videos about Interface Equilibrator, please visit our website.